On May 1st, 2024, a seemingly unremarkable sunspot appeared along the sun's eastern limb. Initially, it didn't stand out, just one of many sunspots that frequently form and fade. But in the days that followed, this sunspot expanded at a remarkable pace, eventually growing to a size 17 times larger than Earth. Scientists named it Active Region 3664, and it quickly proved to be as active as its name suggested. It began unleashing powerful solar flares, some of which triggered coronal mass ejections, CMEs, that hurtled toward Earth. The result was one of the most spectacular aurora events ever recorded, with colorful displays lighting up skies in regions that rarely, if ever, see them. NASA reported that this was the strongest geomagnetic storm in over 5 centuries, so powerful that even underground observatories detected its effects. But the sun didn't calm down after May's dramatic activity. It continued to erupt with M-class and moderate X-class solar flares, keeping scientists and space weather forecasters on high alert. Then, on October 3rd, it launched a massive X 9.0 flare, the most intense in 7 years, right from the center of its disk. Within a week, Earth was hit by a G4-class geomagnetic storm that produced more brilliant auroras in unexpected places and temporarily disrupted radio communications around the world. All of this signaled one thing: the solar maximum was nearing, and now NASA has officially confirmed it. The sun's magnetic field has flipped, marking the arrival of this peak period in the solar cycle. So what does this mean for Earth in the months ahead? How long will the solar maximum last? And perhaps most critically, could this increase in solar activity lead to a rise in global temperatures in the coming year? Though the sun may appear to shine steadily, it undergoes dramatic changes roughly every 11 years in what's known as the solar cycle. This ongoing process alters the sun's behavior, magnetic field, and appearance, and it has a significant impact on Earth. The solar cycle was first discovered in the late 1700s, when astronomers noticed something unusual during their study of sunspots: dark areas that appear on the sun's surface. They realized that sunspots didn't show up at random. Instead, their numbers rose and fell in a repeating pattern over time. Further observation revealed that this cycle occurred roughly every 11 years, leading scientists to define it as the solar cycle. Once this pattern was recognized, astronomers began carefully tracking it. For many years, they monitored solar activity mainly by recording the number of visible sunspots. However, with advances in technology, researchers identified two more key indicators that change during each solar cycle. One is the sun's magnetic field. Since the sun is composed of electrically charged plasma, its magnetic field is always shifting. Scientists discovered that the sun's magnetic field actually flips during every solar cycle. What was once the north magnetic pole becomes the south, and vice versa. This magnetic reversal typically occurs around the time of solar maximum, marking the midpoint of the cycle. The second key change is the level of solar activity, including phenomena such as solar wind, solar flares, and coronal mass ejections, CMEs. These events become most intense during solar maximum and calmest during solar minimum. Thanks to these insights, scientists today study the solar cycle not just by counting sunspots, but also by tracking changes in solar activity and magnetic field polarity. Ever since the solar cycle was first discovered, astronomers have tracked and numbered each one. We're currently experiencing solar cycle 25, and each of the previous 24 cycles had its own unique features. Most followed a familiar pattern, rising to a peak filled with sunspot activity before gradually declining into a quiet phase. However, history records two unusual periods that remain unexplained even today. Just as each solar cycle invites curiosity and fascination with its changing behavior, MOVA globes brings a similar sense of wonder right to your desk. These elegant globes rotate silently using only ambient light and hidden magnetic forces. No wires, no batteries, creating a calming and beautiful scientific display for any space. MOVA globes are available in more than 40 stunning designs, including a space-themed collection featuring planets, moons, asteroids, and constellations. It's a great way to keep your passion for space alive every day. And for viewers of this channel, there's a special offer waiting just for you. The first mysterious period of low solar activity is known as the Maunder Minimum, which lasted from 1645 to 1715. During this 70-year span, sunspots nearly vanished, with only around 50 recorded in total, far fewer than the thousands usually seen in a single cycle. This prolonged solar lull coincided with the Little Ice Age, a time when global temperatures dropped. Rivers like the Thames in London, which rarely freeze, turned to ice, and Europe experienced a series of bitterly cold winters. Another similar phase, the Dalton minimum, occurred from roughly 1790 to 1830. Though not as extreme, it also featured reduced solar activity and overlapped with a period of global cooling. Volcanic events, such as the massive eruption of Mount Tambora in 1815, played a role as well. That eruption led to the infamous Year Without a Summer in 1816, which caused widespread crop failures and food shortages across Europe and North America. More recently, Solar Cycle 24, which began in 2008, stood out for its weakness. Both sunspot counts and solar activity were significantly below average, making it one of the quietest cycles in over 100 years. Its unexpectedly low activity, including fewer solar flares and coronal mass ejections, puzzled scientists and sparked renewed interest in understanding what drives changes in the sun's behavior, and whether we could be headed for another prolonged solar minimum like the Maunder minimum. When Solar Cycle 25 began in December 2019, experts believed it would be even weaker than the previous one. However, that prediction turned out to be incorrect. Solar Cycle 25 has far exceeded expectations. By August 2024, the average daily sunspot count reached around 299, more than twice what scientists had forecasted. This level of solar activity hadn't been seen in over 2 decades. One of the most surprising aspects of this cycle is that its peak arrived earlier than expected. Initially, scientists projected the cycle would hit its maximum in July 2025, with a peak sunspot count of about 115. But in January 2024, NOAA's Space Weather Prediction Center revised its outlook, estimating the peak would occur sometime between January and October 2024, with sunspot numbers ranging between 137 and 173. Then on October 15, NASA officially declared that the sun had entered its solar maximum phase. However, this announcement doesn't mean we've already seen the peak of solar activity. Reaching the true maximum can only be confirmed after scientists observe a steady decline over time, which may take months or even years. So far, solar activity has been notably high over the past 2 years, with frequent sunspots signaling an active period. Researchers now believe the sun will remain in this heightened state for roughly another year before it gradually transitions into the quieter solar minimum phase. This suggests that the months ahead could bring intense geomagnetic storms and remarkable aurora displays. Throughout history, powerful solar storms have had significant effects on Earth. One of the most well-known events is the Carrington event of 1859, the most intense solar storm ever recorded. It occurred on September 1st and 2nd, when British astronomer Richard Carrington observed a massive solar flare. Just a few hours after the solar flare, a coronal mass ejection, CME, hit Earth, triggering a powerful geomagnetic storm. Telegraph systems throughout Europe and North America malfunctioned. Some operators reported being shocked by their equipment, while others noticed that their telegraphs continued to function even with the batteries disconnected, powered solely by the electric currents induced by the storm. The aurora borealis stretched unusually far south, reaching the Caribbean and lighting up the sky so brightly that people could read newspapers outside at night. According to NOAA, gold miners in the Rocky Mountains awoke and began making breakfast, mistaking the aurora's glow for sunrise on an overcast day. 2 telegraph operators on the Boston-Portland line managed to communicate for 2 hours without any battery power, relying entirely on the electrical energy from the storm. They even noted that the signal quality was better than when they used batteries. Another major event occurred in May 1921, known as the New York Railroad Storm. It was the most powerful geomagnetic storm of the 20th century. Although satellites didn't exist at the time, the storm still caused significant disruption to electrical systems. A notable incident was a fire at a railway station in Brewster, New York, and widespread malfunctions in railroad signaling across the northeastern U.S. Later, in August 1972, another massive solar storm struck Earth between NASA's Apollo 16 and Apollo 17 lunar missions. This solar event was so powerful that, had astronauts been in space at the time, they would have been exposed to fatal levels of radiation. The magnetic surge was so intense that it even triggered unexplained underwater mine explosions off the coast of Vietnam by activating their magnetic sensors. Then in March 1989, another major solar storm caused a massive disruption to Earth's growing electrical infrastructure. In Quebec, Canada, the storm led to a widespread blackout, cutting power to roughly 6 million people for over 9 hours. The event destabilized voltages and damaged transformers across North America, revealing just how vulnerable modern power grids are to solar activity. In response, the energy sector began implementing stronger protective measures. Fast forward to early 2022, when a solar flare caused geomagnetic disturbances strong enough to destroy 40 newly deployed Starlink satellites. With today's deep reliance on satellites and technology that depend on a stable magnetic environment, such space weather events pose a growing risk. A significant disruption could cause damage in the trillions and seriously affect systems that support modern life. In fact, if a solar storm similar in strength to the Carrington event happened today, experts estimate it could cause between 0.6 and $2.6 trillion in damage in the U.S. alone. And that leads us to a vital question. Does increased solar activity play a role in Earth's rising temperatures and global warming? During periods of solar maximum, the total solar irradiance, or the amount of solar energy reaching Earth, does increase slightly. This can cause small, short-term changes in the climate. However, these changes are minimal and don't significantly influence global temperature trends. This graph illustrates the link between solar activity and Earth's temperature up to the end of the 20th century. While the solar energy Earth receives has continued to follow the sun's natural 11-year cycle of slight fluctuations, there's been no overall rise in solar output since the 1950s. In contrast, global temperatures have climbed sharply over the same time, showing that the sun hasn't been the main factor behind the recent trend of global warming. Increased solar activity can also affect NASA's Artemis missions to the moon. Mission plans clearly state that launches should avoid periods near solar storms, since the high-energy particles they release can interfere with spacecraft electronics and disrupt radio communications, possibly making it impossible to stay in contact. Interestingly, there's a hidden benefit to heightened solar activity. During these active periods, the sun's stronger magnetic field helps protect Earth and orbiting satellites from cosmic rays that originate outside our solar system. So, while solar storms can be dangerous, the sun's increased activity also acts as a natural shield, reducing the threat posed by damaging cosmic radiation. One of the most thrilling aspects of the solar maximum is the increased chance of seeing auroras. When a coronal mass ejection strikes Earth's magnetic field, it triggers a stunning sequence of events. Our planet's magnetic field usually deflects much of the incoming charged particles, acting as a protective barrier. However, when the magnetic fields of Earth and the incoming solar storm align, a channel forms that allows charged gas to flow directly toward the sunlit side of Earth's poles, sometimes producing the rare phenomenon of daylight auroras. As the storm progresses, the magnetic field stretches outward like a pulled elastic band. Eventually, it snaps back, directing the solar particles along magnetic field lines toward the nighttime poles, resulting in the iconic nighttime auroras. While green is the most familiar auroral color, especially strong storms can also generate vivid red auroras. These color differences arise from the type of atmospheric particles involved and the altitude at which they interact. Green auroras occur when solar particles collide with oxygen atoms between 100 and 300 kilometers above Earth. The more elusive red auroras, like those seen in May, are produced when those collisions happen higher up, between 300 and 400 kilometers. For red auroras to be visible to the naked eye, they must be around 10 times brighter than green ones, making them especially rare and awe-inspiring. Top locations for aurora viewing include Canada, Alaska, Iceland, Norway, Sweden, Finland, Greenland, Tasmania, and the southern parts of New Zealand, places where the night sky regularly becomes a canvas of natural light. As the solar maximum approaches, it's a vivid reminder of our connection to the vast and ever-changing cosmos. an invitation to pause and reflect beyond the everyday. And just like the auroras, MOVA globes bring the wonder of space into your life. Be sure to check out the link in the description and bring home a piece of the universe.